Thanks for joining me. The topic for today's talk is enterprise vector-based information retrieval and prompt engineering at scale using open source technologies on AWS. I'm just glad to be doing this in person, so I don't have to worry about my cat jumping on the keyboard. But before I get into the talk, I want to do a quick show of hands. How many people in the room have actually heard of Retrieval Augmented Generation? Okay, so quite a decent amount. And then how many of you have actually played with it, done some actual work with it and kind of get what RAG is? Okay, fair enough. Great. So yeah, we do have a packed agenda today, and I will be discussing the challenges and opportunities for the enterprise when it comes to generative AI, and then deep dive into vectorized information retrieval using the RAG architecture, Retrieval Augmented Generation architecture. And then I will describe the role of Ray in addressing the scaling challenges that are encountered in the RAG architecture. Stick around till the end, because I will end with a demo. So when we are building these RAG applications or chatbots, enterprise chatbots or agents, achieving quality user experience is being able to provide very high quality results in the least amount of time possible, regardless of the size of the user base. So what you'll see is that when you're building these applications, what it comes down to is this causal interplay of scale, latency, and accuracy. And when you're building these applications, you're trying to find an optimum or an optimum, what I'm calling a global optimum, because I'm taking this graphic from a gradient descent example. But you're trying to balance these factors out, and you have to pay each of these different dimensions attention in order to get optimal user experience. So there are many challenges when you're dealing with these large language models. Large language models are the core of what's sitting at the generative AI applications. There are only a subset of the challenges that I introduce here, which are relevant to RAG in particular. So number one, and the most important one, is hallucinations. So likely you're already aware of hallucinations in large language models. But basically, the idea is these LLMs are trained on very large corpus of data. And they perform really well, near human level accuracy, if you ask them questions that are contained in the training data set. When you ask these LLMs questions that lack context from private data, let's say enterprise data or something that it's not being trained on, that's when it starts to provide, give these spurious kind of results that are known as hallucinations. And there's an example there of ChatGPT talking about a New York Times article that does not exist. And then also, sometimes LLMs may be subject to not being able to tell fact from fiction. So taking a movie storyline and actually thinking that happened in real life when it's just basically a fictional plot, right? So these are real challenges with LLMs. And what's interesting is, so how LLMs are trained on there are billions of parameters, and it can be a few hundred million to over 100 billion parameters. And generally, the idea is that the more parameters the model is built on, the more accurate it will be on known tasks. What's interesting is that the bigger the model gets, the worse the hallucinations get. So if the model is bigger in size, it's supposed to be more accurate. But if you ask it questions on data that it's not being trained on, it'll hallucinate more than a smaller model. So there are these academic studies that have actually quantified these hallucinations. So we are seeing these U-shaped and inverse U scaling trends, where these models are basically less reliable or there are scaling trends that are less reliable at predicting the behavior of large-scale models than previously understood. So behind every successful machine learning model, there's data. It's an old saying, right? And Gen AI is no different. So enterprise generative AI applications need access to many different data sources, including the internet or even just enterprise data, which is sitting inside your VPC or inside your cloud environment. The data that is going to be fed to the model as context can get quite large and quite fast. And so there should be a mechanism to even scale what we call the embedding process. So basically, we are taking all this corpus of data, we're converting those into vector embeddings that we're going to store into like a vector database in the typical RAG architecture. So that can actually get really massive as you start to scale up the number of data sources. Also, when you start exposing these applications to a larger user base, you will need to account for the query per second throughput that your application is providing. So every LLM's behavior varies slightly depending on the purpose that it's serving. In this talk, I will be specifically talking about this very popular pre-trained LLM from Meta called Llama 2. So there's some considerations here. So I mentioned the inverse scaling law. Obviously that becomes very apparent if you're actually monitoring the accuracy and perplexity of the output from the LLM. And then there's also the ordering bias. So what you see is, this is kind of the inverse of the inverse scaling law, where you see smaller models, when they retrieve information from vector databases, let's say they retrieve like the 3 top results, they tend to prefer based on the ranked order of the results, they tend to show or prioritize those at the output as the output to the end user, which may not be always correct. And then in terms of the infrastructure itself, there are some, obviously these LLMs need a very, they need large infrastructure, they need machines with very many GPUs. There are some recommendations that I've mentioned here. These are actually from Hugging Face. They can be not easy to find. So for example, if you are dealing with a 7 billion parameter model that can sit on a medium-sized NVIDIA A10G instance, but as you start to scale up, you'll see that you'll need many more machines, many more instances, which can be not that easy to find. We at AWS are also starting to, we actually released the Llama 2 support on our AWS purpose-built processors for generative AI. We just had a talk about that. We will also mention that in the keynote tomorrow. But here I'm talking about NVIDIA instances, specifically also on AWS. And then so the output from the 70 billion parameter Llama 2 model is excellent. It's if we take it into context of GPT-4 that everybody knows about, it can reach similar near human factuality levels. And there's a graphic that shows how good Llama 2 70 billion parameter model actually performs in comparison to GPT-4. So you can see it's actually pretty close or even better in some cases. And all of these, what I've mentioned, are they are not considering quantization, which I will talk about in detail in the next few slides. This is Inferentia 2 is what we just released the Ray support for Inferentia 2. So if you are building these LLM-based workloads, you can now use Ray for scaling these workloads on AWS purpose-built hardware for specifically for serving. There's Inferentia for serving, and then for model training, there's Trainium. There's still work going on, and we will, we plan to get Ray working for training, model training on Ray Trainium as well. But this is specifically for serving. You can see that compared to the A10G processors that I just talked about, which was one of the recommendations for serving Llama 2 models on Hugging Face, Inf2 actually perform better and provide better latency and throughput compared to the G5 instance types, which are backed by NVIDIA 10G processors. And so, yeah, quantization is an important technique when we are talking about scaling. So there are really two types of quantization techniques. There's there's the one that is used when you're actually training these pre-trained models, and then there's a post-training quantization technique. The post-training one is more applicable in the RAG architecture. You can see here, this is an actual graphic of what I'm going to show you in the demo. When I took a 13 billion parameter model and I loaded it onto a single G5.8x large instance without quantization, the GPU utilization was 94%. When I did add the quantization, it went down to 47%. In short, basically, quantization reduces your memory requirement and also uses less power for your application. And then I'm not going to go too deep into this, but essentially, since everybody already knows about RAG, but this is a pretty standard RAG architecture. We're also starting to see evolution of these autonomous and semi-autonomous agents that are powering different parts of the RAG architecture. And then in order to actually improve the user experience and keep it conversational and improve the response time, we need the ability for the model to keep short-term memory of the interactions with the user. So that's where it's important to introduce cache. So outside of just having the long-term storage for vector databases, you also want to cache these results. So when a user actually queries, if there's a cache hit, you'll see that there is, I'll show you actually that there's the latency is greatly reduced. And then as you are scaling up, so you want to scale up independently the embedding process. Like I mentioned earlier, you might actually land up embedding a large corpus of documents. And then you want to scale up the inferencing as well. So as you start surfacing these applications to a larger user base, you want to be able to scale up both. So Ray provides a perfect API or perfect solution for this. So there's a Ray core that will parallelize these tasks. And then there's Ray Serve, which is Ray core, which would parallelize the embedding process. And then there's a separate library, Ray Serve, which helps in building online inference APIs. And you can scale up just the serving layer using Ray core or Ray Serve as well. So the demo that I actually built is including Llama 2. It's built on Llama 2. The orchestrator that I'm using in this case, if you see that image, the LLM orchestrator is using LangChain, Ray for scaling, and then I'm using the Pinecone vector database for the inferencing. Okay, good. So so talking about Ray for a little bit. So it's really easy to go from like a single node into like a cluster mode using Ray. So let's say if you have like a Python function or a couple of Python functions like that. In order to, let's say you want to distribute this, number one, you need a Ray cluster. So you can run this Ray cluster on many different infrastructure types. You can have this Ray cluster running on EC2. You can have it running on Kubernetes, on EKS, on AWS, or on any scale, obviously. So basically what you'll do is you will add this decorator ray.remote, and then you will add an extension to your actual function to call that decorator, right? It's really that simple. And then there are also, you can provide at a granular level, like how Ray is different from Spark, is that you can gracefully provide the number of GPUs you want to use for that process, number of CPUs you want to use, and you don't have to just think about scaling from machine to machine. You can actually think about scaling at a processor level at the number of cores you want to consume for a particular process. So, and then you can also, like there's purpose-built array libraries for the kind of accelerators that you're using. So if you're using, for example, A100s, you can provide that to Ray and you will get optimizations there. We also recently announced, and we will actually have that announcement officially in tomorrow's keynote, where Ray will automatically also recognize the Trainium and Inferentia accelerator types. Like I said before, Trainium and Inferentia are AWS purpose-built processors for building generative AI applications and hosting these large language models. So training and serving these large language models. So just some numbers here. So if you don't do, for example, any caching or quantization, running on a single core G5.8x large instance, which has 32 gigs available GPU memory. If you take a basic system prompt with a basic query, such as give me some more information about Ray, we are seeing GPU usage of 94% and RAM usage of 20 gigabytes, and takes about 26 seconds to run that query. That same query, if you quantize the model, runs in a fraction of a time. We're talking 4 seconds comparatively. And the GPU usage also goes down by 50%. And the RAM usage goes down by less than 50%. Now, what's interesting is, when you're actually building this enterprise chatbot, you would want to not always hit the endpoints and add latency to your serving layer. So that's where I mentioned the caching layer. So you would want to have results being surfaced from the cache, and you'll see dramatic improvement in latency there. So instead of 4 seconds to answer that query, if you just pull it from the cache, it's sub-second latency, right? Similarly, as if you provide a deeper query, so when you say depth 1, so when the model is actually having to go, or the vector database is actually having to go and find a child web page of the parent web page, so depth is greater than 1. So you start seeing the latency go up a little bit more. And then when you start doing actual prompt engineering, right? So you're prompt tuning and you're providing different kinds of prompts, such as you want your model to write the code. So that's when you really start seeing the latency go up. And that's also because the model is trying to now meet its maximum token limit. So in the previous queries, which are simpler, you get results which are like 128 or less number of tokens or the words. The token size or the maximum token limit in this case that I'm using is 512 tokens. So when you get a response, the model will max out after producing 512 words in the response. So that's where it's actually maxing out when you're providing these more difficult, more elegant or more complex prompts. But you also see like a scaling trend. So the model actually gives you better throughput when you ask for these more complex queries than just returning simple results. So this is, you can see the highest throughput that I was able to get before optimization, which is not using caching, not using quantization, was about 1.6 tokens per second, which is similar to the speech of an average American. An average American, the rate of speech is about 2 words per second. And then if I did add quantization, that's when it went up to 25 tokens per second, right? Which is still in kind of the human realm, but much higher. And like we have to consider these factors when we are building these applications for the end users. And then with purpose-built hardware, like I mentioned before, we are seeing what I call para-human response rates, which is like we're completely blowing into hundreds or even thousands of tokens per second range. Those are based on studies. I haven't personally tested that, but it's just interesting to see that kind of advancement and evolution is actually happening. Okay, so I'm going to go into a demo of this. So this will be on GitHub. You can find this on my GitHub repo. And it's purpose-built, so if you have a Ray cluster running, you can just run through this demo yourself. So essentially, what I have here is I have a Pinecone database running in the backend. So let me show you the architecture again of the application real quick. Yeah, so there are basically two parallel processes here. One is you actually build the enterprise knowledge repository. So think like if you are a car company and you want to have very specific information about your car fed to the model. So if your end customers ask you these questions, it doesn't have to go through, the model does not start to hallucinate and provides accurate responses. So that's where you go through the actual hydration of the vector database itself. In my case, I'm actually going to take data from a URL directly, and without having to download it, I'll just create the embeddings and upload them directly onto the vector database. And then you have a parallel pipeline where, which is the user experience, right? Which is the application that you surface to the end user. And that's where you take these embeddings from the vector database. The model, uses these embeddings and crafts a response, which is then provided to the end user. There's a cache lookup that is introduced in the middle to improve the latency. If the query has not been asked to that model before, it will go to the embedding process, and that query's response will be drafted by the model and sent to the cache storage, right? And then the next time you ask that query, there's a cache hit, so you get that query directly, or the response for that query directly through the cache. Now, there's going to be significant, work being put into this caching layer as well. For example, right now, it has to be the exact query for the cache hit to actually happen. But in the future, you will see that like how the vector databases actually calculate similarity indexes between the corpus and the query. You will see that there'll be a similarity score that will be calculated between queries. So if a query matches previous queries, even though they are not worded exactly the same, you'll be able to get a successful cache hit. So yeah, I just have a Jupyter notebook here. In order to run this demo, there are a few different requirements that you need to have. You need to have the Hugging Face, the library, the Transformers library. I'm downloading Llama 2 or using Llama 2 directly from Hugging Face. There is bits and bytes for the quantization of the model itself. Since I'm using Pinecone, there is, I need the Pinecone client, and obviously LangChain, which is the orchestration engine here. So first things first, like we create the Pinecone embeddings. So here, I basically initialize the Pinecone client. I have some Pinecone related credentials. Oh, I'm sorry, I'm not actually sharing. Okay. Let's scale back up. So yeah, the requirements file. So I have the, obviously the Hugging Face library where I get the Llama 2 model from, the Transformers library, the LangChain, which is the orchestrator here. And then there is bits and bytes, which I use for quantization. And the first notebook that I'll walk through is basically, hydrating the vector database with certain information, like which we want to query from the model itself. So initially, I initialize the Pinecone client. I need some credentials here, such as the index name of the Pinecone database, and some other credentials in the API key. Then I initialize Ray. I'm going to be using a Ray cluster here. My Ray cluster is actually, it's backed by NVIDIA 10G processors. It's the G5.8x large that I'm using. You can see the GPU here. This is the Ray dashboard. You can see the GPU, and you can see the breakdown of all the processes here as well, along with the error logs and the stack trace. So pretty nifty tool. And then I provide the URL. So here I can give SageMaker or any online documentation that you want the model to not necessarily train on, but to basically look up when it's providing the responses. And then when I do the recursive URL loader, I can provide the max depth. So that is like how deep inside the web page do you want the vector database to go to create these embeddings. And then instead of having to download all this data, which is pretty common, you can actually now upload the data directly into the vector database using this recursive URL loader. And that's exactly what I'm doing here. I use the Hugging Face mini LM model, which it's actually a very small size model and works pretty effectively. And it takes about 8 seconds to load this data into my vector database. Basically, I want to parallelize this process, right? So as the amount of data that I want the model to look up, as that starts to grow, you want to be able to gracefully parallelize this process, and that's where Ray comes into play. And like I mentioned, you don't have to, I come from the world of big data like Spark and Hadoop. The big challenge of big data was that there was this property of oversubscription of cluster resources. So with Ray essentially solves that problem because you can granularly describe exactly how much resources your individual processes should be using. So in this case, for example, since I just have this one repository, I don't need to use one entire GPU. I can only say just use 1/10 of the GPU. And that way, if I were to use, let's say, an entire GPU, I could parallelize 10 different processes on a single GPU as well. And that's exactly what I'm doing here. This is a function that I create, similarly to what I walked through earlier. I initialize the Pinecone client. This is where I actually drop the embeddings into Pinecone inside this function. And I mean, it's a typical Python function. There's no change in the function. The only thing that I'm doing is adding this Ray remote decorator. And then finally, I say how many shards I want. So in this case, I want to parallelize. Let's say I had 8 different repositories, right? I had Ray, SageMaker, Bedrock, all kinds of stuff. And I wanted to parallelize that process instantaneously. I can say the number of shards, and then I have this function that splits the embeddings into these shards. And then when I call this function, process shard, and I just, instead of like a typical native Pythonian call, where I would just say process shard, shards I, and embeddings, I just say process shard dot remote and pass those arguments, and that's it. And that's when it's going to start running through the Ray cluster. I'm not going to run through this in the interest of time. Basically, we have about a minute and a half left, but you will start to see these, different threads hydrate when I would run through that function. And I'm able to parallelize this, and I'm actually able to view the amount of resources that are being consumed by the cluster as well. Once this is done, the next step is to actually query the results. So, let's say, so there's some issue here, but yeah, I want to point to, in this case, I want to, I'm using Ray serve. So the model is actually loaded to the Ray cluster, and Ray serve, with what Ray does, it parallelizes your requests. So I can ask these queries now specific to Ray from the model, and this is data that it wasn't actually trained on. So I talked about how the latency went down when I quantized the model. I showed you that graphic. It'll go further down if this query was cached. But here you can see, like, I'm asking a more complex question rather than how does Ray parallelize computations across instances. I'm asking what is an actor pooling strategy in Ray. It gives a response in 13 seconds. Then I pass a prompt, explain in detail the actor pooling strategy in Ray, and that's where it gives me a more detailed breakdown response. And then I say act like a programmer and break down various steps, right? So I have a function x that calculates a square of the input, and can you parallelize that function using Ray and give me the code, right? And that's exactly what it does. It breaks down the code. I could even say, hey, provide me that code in JavaScript or in Python. Ray has APIs for both, and it would give me the right results. And I mentioned the token size. You can see the max token size here is lower, and you're getting a response in, let's say, 13 seconds. This is where it's actually going through the entire max token size of 512 tokens, and that's where you actually start seeing it scale slightly better. So, okay, we're up on time, but yeah, thanks so much. And if you have questions, just grab me on the way out.